Hi, welcome to this afternoon's presentation on the space threat OODA loop. My name is Tom Johnson. I'm Vice President of Engineering here at AGI. And we're going to be covering sort of our view of how this has evolved and looking at the OODA loop in the context of space activities. Try to factor in some of the lessons that we've learned from our own experiences with the Commercial Space Operations Center that we run, as well as in our interactions with and supporting our different customers. So let's set some context for why we think this matters. What you're seeing here is a graphical representation of the time history of a Russian spacecraft called Luch as it's been moving through space over the last couple of years. You can see on the top is a pictorial representation as it's moving across the geobelt, and you can see a graph of the longitude as a function of time on the bottom. And what we see going on here is that the Luch spacecraft is moving around at the geobelt, parking next to different spacecraft in geo for reasons that are really not quite well understood. It's not supposed to be there, but it's moving around, and it parks next to these spacecraft. What we think is going on is it's parking close enough to be within the uplink antenna pattern, and such that it can perform signals intercept activities to listen to the signals and receive the signals that are being uplinked to these spacecraft. This has been going on now for quite a few years, and we continue to track it as part of our processing in the ComSpoc. But it's this kind of activity in space that really sets the tone for trying to understand what's going on and what can we possibly do about it, and that's where the OODA loop comes into play. So what is the OODA loop? It stands for Observe, Orient, Decide, and Act. And it comes out of the fighter pilot community. Primary creator of this was a pilot named John Boyd in the U.S. Air Force. He's trying to help train and understand what is the process a fighter pilot goes through as they try to fly their aircraft, accomplish the mission. So there's four primary steps. Let's talk about observe. We need to get the information into the pilot, or in this case, into you as the operator of a SSA system or whatever it may be. That could be sensor data from, say, a radar, or it could be your eyeballs. It could be your instruments on your aircraft. It could be the data can be coming in from a variety of sources, but you've got to observe what's happening now. Where is the other object, or the other pilot, or the incoming missile, or whatever it might be. I have to observe the environment that I'm operating in. I'm about to head into cloud cover. In the context of space, am I in a high drag regime? Am I in a low drag regime? Am I lit? Am I not lit from the sun? All these different kinds of things that start to become factors. Then we take all that information and we go into an orientation step where we have to assemble it all together and come up with a coherent picture of what do we think is going on. With that information, we can now move to the next step of how to decide what is my next step. And then you take a look, explore all your options. In the context of a fighter pilot, it might be bank left, bank right, throttle up, throttle down, fire a missile, change my approach strategy, whatever it might be. For space threats or space actors, it might be, do I need to have move my satellite? Do I need to change the orientation of my satellite? Do I need to jam somebody, or do I need to worry about jamming? There could be a number of different options. So as you go through the decision process and you're coming up with your different hypotheses on what you might do, and then obviously at that point you choose one, you act on it, and then the process starts over again. I make a decision, I act, and then I start collecting more data to see how the situation is now responding to my choice of decisions. So let's take a look at that in the context of space. Okay? So when we're talking about space, in particular space situational awareness, we're looking at, we've tried to break up the tasks that we routinely have to do for doing SSA and put them into the framework of the OODA loop itself. So let's talk about the observe step. For space activities, that really comes down to sensor tasking and scheduling, and we'll go into more detail on each of these. And then the actual observation collection. So the first step is, what do we want to do? Second step there is, how are we going to actually do it? And then there's the orient part. Now that I have sensor data, what do I want to do with it? For SSA problems, I have to go through what we call the observation association process. I have to deal with uncorrelated tracks. I have to deal with potential maneuvers that have occurred and trying to figure out if there is a maneuver. I need to do conjunction assessment to understand the relationship between objects. I have to do threat assessment to try to figure out, is this other object a potential hostile object, or is it a risk to me in some manner? It may not necessarily be purposely hostile. And then I had to decide my COA, my course of action. Given all this information, what do I do? And then actually execute the COA. So we're going to take a look at this now and go into more detail on these, and again, talk about some of the lessons that we've learned over the different years. Okay. So the challenge here is there's a lot of steps in this process that we're trying to run. Okay. Some of them, if not done carefully, can take a long time to complete. And if, depending on how long it takes or how complicated that step is, you can essentially leave yourself vulnerable because you're spending too much time trying to assimilate data before you have a chance to act. So in a perfect world, you'd have all the time in the world to say, I'm going to get all this sensor data, I'm going to get a perfect picture of what's happening, I'm going to make the perfect decision, and then I'm going to be completely safe. Of course, nobody actually told the other guy that you want all this time. So the other guy is purposely trying to break your OODA loop cycle by acting in a manner that's faster than you can process. So if it takes me 15 hours to get my perfect sensor picture of what's going on, and the hostile or the other actor knows that, then what they're going to do is they're simply going to say, well, I'm not going to wait for you to have a perfect picture. I'm going to act in 2 hours. And if I can keep messing up or interrupting your OODA loop cycle, then the other actor is going to win. Okay? So that's the challenge. We can't take forever to do this. We have to act in a timely fashion. So it comes down to, how do I compress that cycle time such that it's meaningful? You know, obviously in a fighter pilot type situation where it's highly dynamic, you know, this could be happening in, you know, in the context of seconds or minutes, you know, depending on what's going on. If you're, say, in a dogfight. In space, things tend to not be that dynamic, but nonetheless, we may not have hours and hours and hours to execute this process. So these are our top 5 recommendations, and we'll dig into these in more detail. Let's start at the top, which is sensor scheduling. You need more effective algorithms to say, if I don't have a magic pot of money to field an infinite number of sensors, how do I best take advantage of the sensors that I do have and sort of optimize and get the best bang for the buck there? And so a lot of that comes down to, are you scheduling or are you tasking? And we'll explain that in more detail. The second step recommendation is to please, please, please fuse all possible data sets. We've seen too many times where there are disparate data sets that on their own are okay, but had we been able to bring them all into one place and actually combine them and process them all together, you really would have had some very powerful analysis results that would have greatly improved your ability to execute the OODA loop and make high quality decisions instead of maybe decisions on low quality info. You need to use algorithms which inherently support rapid event detection and characterization. So for instance, if a spacecraft maneuvers, it could be critical that you know about that in a very near real-time situation, because you may not have a lot of time when you decide to act on that information. For instance, if you need to fire a thruster to maneuver your spacecraft, it may take time to configure the spacecraft correctly. It may take time to get authorization to do that in the first place. And it may take time then for that maneuver to actually build up enough delta V to be relevant. So I need to be able to detect the other maneuver in a very timely fashion and so that I can execute the rest of my OODA loop. Then there's threat analysis prioritization. As you're trying to look at all the potential threats, you know, the other actor may not be broadcasting, hey, I'm the threat guy, and you know, and we all know that. So you have to pick out the threat from the sea of normality and normal things that are going on and try to identify which things are potentially of interest, which actions are of interest, and which ones are potentially hostile, or at least things that you might be concerned about and evaluating. So you need to be able to prioritize and crank through this in a very timely fashion, and having people in the loop trying to do this manually is not an effective strategy. So as you learn more and more about the threats and the problems, you need to start automating this stuff so that it can happen in real time and not have people in the loop. And then you need to be able to evaluate your courses of action so that you can then make execution decisions. So your analysis tools need to not only support what happened in the past, but you've got to start being able to do predictive analysis to understand what are potentially going to happen in the future, because that may affect my decision. And again, that's got to be happening rapidly so that you can then inform the COA decision process to say, here are the problems, here are the potential threats, here's how we think this might evolve, and then what can we do about it when we start making decisions. Okay, so we're going to talk about sensor tasking and scheduling first. Okay? So first we need to make sure we understand the difference between these two terms. Tasking is when some central authority reaches out to the sensors and say, here's what I would like you to collect. This object is a priority A object, this is a priority B object, whatever your criteria might be, and it's a request for collection. But the sensor is going to operate and try to respect that request, but it may have other things it has to do. So take, for instance, a missile warning sensor, and say it's a radar. Okay? The primary mission of that radar is missile warning, and space track is a secondary mission. So as you look at what that radar is trying to do, and it's allocating power and maintenance downtimes and everything else, it's going to say, I can't compromise on missile warning, so if I can get a chance, I'll try to collect, but I may not get it. Or if it's a telescope, it may be trying to operate, and it might choose because it might be doing other missions like some research stuff or anything else, something else. And so your collection strategy, your request might not be the highest priority. Okay? So tasking is asking the sensor to do something. Scheduling is when you take a look at what the sensor capabilities are, what your spacecraft are doing, and then you make specific requests out to the sensor. And you say, I want you to collect on this object at this time from this sensor. Now, if you can get that specific, you can really optimize things and really start to maximize your sensor utilization, because you can now pick the right sensor at the right time for the right object, such that you can collapse the orbit covariance on that object in an optimal manner and minimize the number of tracks that you have to get, or make sure you observe it very quickly after a maneuver or during or after potentially a predicted maneuver. Okay? But scheduling requires much more control authority over your sensors. So it kind of depends on the sensor network that you're working with and what their priorities are, how much of this you can do. Okay? In general, our recommendation, of course, is to prefer scheduling. But that's only possible if you have this sort of exquisite top-level control of the sensors. So the problem with tasking is that you tend to get limited observability of an RSO, or a resident space object. So for instance, we've worked with some sensors in the past. They were exquisite sensors, but unfortunately when tasked, they would say, we want a collection on object A. They would say, great, I'm going to come up on that object every night. It'll be the first thing on my list because that's a high priority request. But the problem is that's a geostationary satellite, and when I track it, I'm getting essentially the same observation of the same part of the orbit every day. And all I really know about now is where that spacecraft is at that time of day, every day. And matter of fact, I may not even be able to tell that it's a geo, because it turns out an object with a period of 12 hours will also show up in that same spot every day at that time. So you need some diversity in your measurements and in your scheduling. And if you just make a tasking request, you may fall into a trap of not actually getting what you wanted, although you got what you asked for. So you need to make sure that you really communicate your needs out to your sensor partners. Near real-time scheduling can be difficult. So for instance, you have the perfect master schedule, but then Murphy's Law comes into play, and it turns out that your telescope can't operate because there's cloud cover, the humidity's got too high, you lost power and your backup generator's dead at your radar. All these things happen. So you need to sort of be able to readjust the schedule on the fly. So having the perfect scheduling algorithm is not the whole part of the story. We need to actually be able to respond and adjust in some manner to the real-time issues. All right, so the next step is observation collection. We've put out our schedule, our tasking, we're getting data in, and we want to take a look now at some of the challenges there. Every sensor has its unique problems and obstacles. And they have to be factored into your overall strategy and plan. So optical instruments, if they're on the ground, so typically a telescope or even a laser ranging system, you're fighting weather issues. Okay? Cloud cover is a problem, humidity is a problem. These are things that all have to be, planned around or dealt with. Then you have planned and unplanned site outages. Right? This happens to every package or every instrument or sensor that we have. So those outages can be something as simple as I've lost power. Okay, well I can try to mitigate that. I'll have backup power, or I'll have an UPS, or and you can start to you can throw money at some of these problems and try to make them go away. Do I have internet connectivity or somehow some other data connectivity to get the data back to me? How much bandwidth do you have? What's your backup communication link look like? And there's been things like, we've had lightning strikes knock out a power line and all the fiber optics for a whole part of a country. And our sensor went down in the middle of that. Didn't see that coming at all. So you have to have redundant sensor coverage as well to help mitigate the things that you can't predict. Things like 12 inches of rain causing a landslide and wiping out the road and all the power to your site for 3 days. That wasn't in our predictive sensor model either. Then you have to deal with the constraints on your sensors. So your radar theoretically might be able to look in every direction, but in reality it can't. It can only put power in certain directions at different times. There is a power budget limit. And so you have to effectively plan your radar tracking strategy to say, where am I going to put my power and how long am I going to dwell in different areas. You have constraints. Just because I have a telescope and it's dark out doesn't mean I can see the object I'm trying to track. How big is it? How reflective is it? What's the solar phase angle between the sun, the satellite, and my sensor? Do I have to worry about things like, is the satellite, when I'm looking at it, does it have the galactic plane in the background? That's a noise source. Makes it difficult to make observations. Is it a full moon out? I can't get within so many degrees of the moon, or it's too much background noise. Okay? Even if it's a parabolic dish, what direction I'm rotating the dish in matters because I've got cabling. I can't keep rotating the dish 20 times in the same way because I'm tracking a satellite over and over, because I'll get cable wrap issues and then eventually something's going to break. Okay? So these are all things that have to be factored in. At top-level system engineering planning, you don't worry about this, but you quickly get down into the weeds. And in order to build an effective observation collection strategy, these are the kinds of things that you do have to worry about. Okay. When you are collecting data, this is some of the experience that we've dealt with, both with our customers, our partners, and our own sensors. You want to collect the data as raw as you can. Okay? And what I mean by that is, in the case of, let's say it's a telescope image, all right, you take the image, you process it, you pick out your spacecraft, and you say, all right, I think it's this right ascension and declination. At that point, stop. Don't do anything more to the data. Just send that data in. Because what we find from time to time is that the sensor operator or owner may try to help you by doing further processing on the data. So for instance, you might have a radar that's tracking something and it's giving you ASL range and Doppler data. Unfortunately, some of the radars will do things like, I'm going to pre-correct the measurements for ionosphere refraction. And so they've changed the range and they've changed the elevation angle to correct for the fact that this is a UHF radar. It's affected by the ionosphere, and that has to be factored in. The problem is if you pre-correct the data, I don't know how you did that. I don't know what model you used, and sometimes the models aren't very good. And unfortunately, I now am in a position where I can't uncorrect it to apply my own model. So the best strategy is always please send the data as raw as you can or as uncorrected as you can. Don't account for light time delay. Let us worry about that. Don't account for troposphere refraction, atmosphere or ionosphere refraction. Please don't try to pre-correct for aberration and other kinds of effects that are going on. Keep the data as raw as you can, because there may be a time, it could even be years from now, where somebody will come up with a better model that we can then try to apply to the data and see if it helps. Okay? But the more you pre-correct stuff, the less opportunity there is for us to undo that and try to maybe try to do something better down the road. Okay? Depending on how much data you're collecting, you may find that it's advantageous to process it locally on site, or at least do some intermediate level processing. So for instance, one of our telescopes in the ComSpoc will typically generate about a terabyte of imagery a night. And it's not very feasible for us to transmit a terabyte of imagery per telescope, out of some fairly rural location where it's nice and dark, and get it to us with any kind of reliable fashion to do processing here. So that's a case where just due to the amount of raw data that's being collected, it has to be processed on site, and we distill that down into the measurements. So we might take a several megabyte image, distill that down into 100 bytes, and then send that out. Okay? But sometimes the communication links are a little ratty, not very reliable, or you can be in that situation. So what you want to make sure is that your system can continue to try to collect even if the link is down, or if the link starts to get backlogged. So we want to be able to say that when the link does come back up, then continue to send the data over to me. It's also useful to archive it locally for a bit, because sometimes you may find that there's been a processing problem, or you want to tweak the algorithm and you want to go back and reprocess the data. So keep it locally, because there are times when we'll look at something in the final measurements that will say, that looks weird. I'd really like to see the raw image that we took to make sure I understand what the software was trying to do, and make sure that do I have a processing problem or a bug, or is there something weird about this situation. So having access to the raw data for at least some period of time, it could just be a couple of days, is a useful thing to do. So now that we have measurements in, we have the problem of observation association. Observation association deals with the issue of, I saw something, but I don't know what it was that I saw. I think it's a spacecraft, I just don't know which one. Okay? But this is, of course, a critical step in dealing with an SSA activity, and particularly with closely spaced objects. So if I think this object is doing something weird, it would be critical for me to know, is that my object? Is it your object? Is it a threat object? Because if I make the wrong association, I may think that an object is acting with hostile intent, and it turns out it's not even something that I care about. Okay? So false identification of threats can lead to an amazing number of problems, the least of which is just confusion. Because you don't know, is this really a threat? Is this not a threat? I don't trust this sensor. I don't know what's going on. I can't make actionable decisions, and you become paralyzed with this inability to know what's going on. Because then when you don't trust things, you start to delay your response because you're trying to wait for more data to sort it out. Now your overall timeline in your OODA loop is starting to stretch out again. It can also lead to false event detection. So you might think, because I've cross-tagged two objects, that one of them is now maneuvering and might be a very significant maneuver. And you might think, oh my goodness, I need to tell people and warn people that this is going on. And it turns out it's not a maneuver at all. You've cross-tagged multiple objects, and it just looks like a maneuver if you did that. But had you actually associated the data correctly, it would have been a completely benign situation. You may also think that your sensor is actually having a hardware problem, or you have a software algorithm issue where you've got the data mistagged and something's going on. And you don't want to miss a threat. So it may also mask the fact that something really is going on, but you can't tell. So either way, trying to solve the observation association problem is really, really critical. And particularly when it comes to maneuver detection, it may also be one of your very first tip-offs that something is going on, because you got an observation that you think goes to satellite X, but your predicted model for satellite X says it should be over here, and it turns out the observation says it's over here. Well, something doesn't line up in that scenario. Has the object maneuvered, or is it a different object? Or maybe it's actually spawned a secondary object. Is it a breakup or something? Or an intentional release? So mistags, this is when we get the observation association problem wrong. Mistags are a fact of life. It happens. Particularly when you have closely spaced objects that can be crossing in front of each other. Like if you're looking at it with a telescope, they may cross in front of each other, and it may be difficult to figure out when they separate which one is which. This happens all the time when you have, for instance, a cluster of objects in geo. It's very common for owner-operators, because of the licensing restrictions and where they're allowed to operate. They may have as many as 6 spacecraft stacked in the same geo slot. And then as you're looking at this from a telescope and they're all kind of moving around and doing their thing and they're maneuvering, the cross-tagging problem can become quite the challenge. And so the ability to have good algorithms to help sort this out becomes critical. And you want to start looking at things like past performance, past maneuver history, to try to figure out if a maneuver occurred or it's a mistag. You want to start looking at things like the visual magnitude signature. If you've got a radar that's tracking something, you can look at the radar cross section potentially, or the range and the Doppler, and you start to look at all the different measurement types to try to sort it out. Of course, you want this as automated as possible, just due to the onslaught of tracking data. As more and more sensors are fielded, there's just so much more data coming in that you can't have a human in the loop on this. The entire process has to be automated. Closely spaced objects require special attention because it's so easy to start to confuse them. When they're separated and you've got some geometry and some diversity, it becomes a much easier problem. So you have to bring in more and more advanced algorithms, and this is an area of constant research, throughout the community, and so it's worth investing in this, because if you get this right, it enables everything else downstream, and if you get it wrong, the rest of your algorithms now have to be more robust to deal with the fact that you may be lying to them. Then we have the problem of uncorrelated tracks. So let's talk about uncorrelated track processing. This is a problem where we have an object or a measurement set that my sensor sees, but we can't map it to an object in our catalog. So that's typically the job of an observation association problem. I get a track in, I try to map it to something in my catalog, but when that fails, that track is now uncorrelated. And so I have to start to deal with these. Now, why would I have an uncorrelated track? The simplest explanation is there's a new launch and there's literally a new object or objects up there in orbit. Okay, great. Then I have to start collecting measurements on it and start to piece those together to make a new orbit for this object. You can also have an on-orbit berthing or breakup. There's really no difference physically between those two activities, except the breakup is typically accidental due to, say, a battery exploding or a propulsion line exploding or what have you. And instead of one object, you might have 20 or 30. A berthing might be a satellite releasing another satellite. So this could be something as simple as an upper stage that then releases its payload or payloads. It could be another satellite releasing a smaller satellite. The ISS is a classic example of this, where what they'll do is they'll bring up CubeSats and then they'll either launch them from an ejector or literally almost throw them out the door. But either way, new objects are being created and showing up in our measurement set. So as these build up, you start getting these uncorrelated tracks. You have to have a process for dealing with them. And you want to start trying to process them to merge tracks together and try to identify, if I put this track with this track with this track, I can now get a good orbit solution, and then I can decide that I think this is a new object and I can add it to my catalog, so that down the road I no longer have uncorrelated tracks for this object. As the data comes in, they'll be mapped to the right object and go. How often you want to do this processing, it depends on your ops cadence. So this might be something that you initiate once a day, once an hour, or just as the operator decides. And it kind of does depend on the situation. So for instance, a new launch where you're expecting 50 new objects to be showing up in your catalog, you might have a very high cadence on your sensor collection because you're trying to initially get those objects. And then you want to run uncorrelated track processing pretty quickly to try to start to sort those out as best you can. And maybe you don't get a solution on all of them, but you might get some solutions on a couple of them that are good. And then you start publishing those, and you continue to refine that as the process moves on. And you have to decide what's your criteria for adding that object to your catalog. Does it always require an operator intervention? Are there other decision points to decide on bringing that object into the catalog, like I know what launcher it came from, or I know what its name is, or whatever it might be? So there's a number of different UCT algorithms available, and again, this is an object of much research, and it continues to be, because as you get more and more sensor data in, and as the sensors become more and more capable, you may start seeing objects that have always been up there, but you just simply couldn't track them before, or you couldn't track them very reliably. And so we want to have more improved algorithms to deal with that and process the data. Ideally, they should be multi-threaded. You're trying to get as much done as you can. These problems typically tend to be parallelizable. Speed is essential. So I can't wait, for instance, on a breakup or a new launch or something. It doesn't do me any good to figure out what happened 5 days later. Okay? That's not operationally relevant in the context of my OODA loop. So I need to be able to get answers quickly and some sort of quality control on how well I believe those answers so that I can then feed that forward to the rest of the team. So now that we have observations and tracks in, we think we know who they belong to, we need to solve the orbit determination problem. How do I process that data to come up with a new orbit solution? So OD is fundamental to effective defensive space control operations. I need to know where everything is, and I need to then be able to use that to predict where it's going to be. And we need to do that accurately. So there's a variety of OD algorithms that are used classically, something like a least squares or an optimal sequential filter. Our experience has been from using both. We prefer the optimal sequential filter, or the simplest explanation would be a Kalman filter. The reason for that is it allows us to rapidly respond to real-time data inputs. It gives us faster maneuver detection and characterization, and we can actually process the tracking data right through a potential maneuver. Classically, when doing orbit determination, you don't want to do a fit across an unmodeled force like a maneuver. So people would stop their OD fit, wait for the maneuver to complete, and then start their OD fit again. That's an effective strategy if you actually knew when the maneuver was, which a lot of times you don't in an SSA environment because nobody told you. If you're maneuvering so often, you never have the opportunity to stop your process and start again. So with the way spacecraft are being built these days, and you take a look at a classic ComSat and GEO now, they might be maneuvering 4 to 5 times a day and be burning a total of 6 to 12 hours a day. So there is no such thing as a maneuver-free period anymore. And in a sense, spacecraft are starting to act more and more like aircraft and missiles. They're much more maneuverable, and relying on pure Keplerian physics and permutations of that to predict what's going on is becoming more and more difficult to do. So you need to have an estimation technology that's more capable than just the classic least squares. Your OD quality also serves as a potential tip-off that something else may be going on. Either a maneuver is in process, or you may actually find that you are having sensor problems, and this can come out in your OD process. So what does it take to be able to really do this well and deal with the OD problem in a sort of a contested, a lot of objects going on, a lot of activity going on? And again, we've tried a number of these different algorithms over the years. The ability to process multiple satellites simultaneously becomes useful, particularly when dealing with closely spaced objects, either in a conjunction sense, where 2 objects just might get close and hit, or in a proximity operation sense where something and one object may be doing proximity operations around another object. If I can process them simultaneously, what that allows me to do is not only understand where they both are, but more importantly, I get a relative understanding of where they are to each other. In particular, I can get a relative orbit covariance, not an absolute one. And the relative covariance may be much tighter and allow me to identify exactly what is going on. So multiple satellites simultaneously is very useful. Being able to process relative measurements is very useful. So sometimes I may be estimating a spacecraft that it itself is observing a second spacecraft, and I can start to do relative measurements between them. You want to generate the full realistic covariance. Every estimation process produces a covariance. It's inherent to the fundamental mathematics. The question is whether you believe it or not. The covariance essentially tells you what is the accuracy of my parameters that I'm estimating. What's my confidence level? And if I don't trust that, then what happens is it no longer becomes an effective tool for decision making. So coming out of a batch least squares process, the covariance is optimistic. It's always too small because the batch least squares methodology only captures the uncertainty contributed by the measurements. It doesn't capture the uncertainty contributed by the force models, the fact that you actually think you know what forces are acting on the spacecraft, but maybe you don't. So there's an uncertainty inherent in all these things, and with an optimal sequential filter, we have a way of capturing that, folding that into the covariance, so that we can then use that to make decisions. You also want to make sure that your OD process can fuse all the measurements into a single estimation run. Sometimes you find that there are tools that will say I can use as-L range or I can use right ascension declination, but I can't bring in time difference of arrival or frequency difference of arrival information because they don't have the right measurement models in mathematics. Well, now you're giving up information. You want to bring all that together, and it doesn't matter if some of the measurements are less accurate than others. As you appropriately characterize and calibrate your sensors, that automatically folds into your overall orbit solution covariance and allows you to take advantage of it. The other problem you tend to run into is it's very convenient to treat that, when doing orbit estimation, to treat things as constants because that makes the math easy. But unfortunately, the other operator may not be doing things in a constant manner. So when I'm dealing with things like my force model, my ballistic coefficient, or my solar radiation pressure, my area is not constant. It's convenient to treat it as such, but in reality it isn't. The thrust that may or may be going on may not be constant. They may be pulsing the thrusters. They may be changing the direction of thrust. So the ability to deal with time dynamic parameters is really important, and we found it very useful when processing data. Okay. So now we have to deal with maneuvers. Active spacecraft maneuver in support of accomplishing their mission. Most of the time it's just a station-keeping activity. I need to stay at this longitude box because I have a bunch of antennas that are all pointed at that box. Or I have to maintain a particular sun-synchronous orbit so that I pass over the same part of the Earth at the same time on a repeated fashion so that I can get good quality imagery. Okay. Of course, maneuvers are also maybe a source of hostile activity. Is somebody trying to maneuver close to me, or is somebody coming at me from a kinetic or some other type of a threat? So I need to detect the maneuver and try to understand what's going on. I also have to deal with the fact that 99% of the maneuvers are benign and I don't care about them, but I still have to model them and deal with them because otherwise they will corrupt my orbit determination solution. Plus, dealing with the maneuvers and estimating them now gives me insight into the overall history of this object, and I can start to establish a pattern of life that then allows me to make predictive estimates as to what we think it might do and when it might act. And if it does or doesn't, that might be a tip-off as to intent or if there's a problem on the spacecraft itself. So maneuver detection is the first step in recognizing that there's potentially rendezvous operations going on, that a spacecraft may be trying to align orbital planes even though it's very far away from you in distance, or initiating proximity operations. Maneuvers can be cooperative or uncooperative. It would be nice if everybody told us the maneuvers they were about to do, because then I could tell my estimator and everything would be great. In a cooperative sense, I have full a priori information about the maneuver. It's going to start here, it's going to stop there, here's the thrust level, here's the direction. That would be terrific. So if you're working with a cooperative owner-operator, you may have that information. But practically speaking, in the SSA environment, you have uncooperative spacecraft. They're not telling you anything. So it's up to you and your algorithms to try to deal with this. You have to try to detect that a maneuver has occurred, and then you have to try to reverse engineer it so that you can maintain track custody of the object. You may not have the best solution, but you need to always make sure that you have a solution so that you can communicate to the decision makers what you think is going on. So now that you actually have orbits and you think you know what's going on, you can start to do predictive analysis. And one of the common things that you do is conjunction assessment. Okay? This is typically done from a safety of flight standpoint. I want to make sure something's not going to hit me. This is usually a problem of debris on active. And I want to make sure as we find more debris, either because we have better sensors or we're just tasking our existing sensors better, we need to be able to understand when an object may be getting close to mine, because I may have to do some sort of mitigation activity to deal with that. And so some people will say, well, I'm only concerned about something getting close to my spacecraft. I'm more interested in debris on active problems. Well, you can also look at everything on everything. That used to be a problem that people would say we can't do that because it's too computationally intensive. But that problem's been solved. Computers are cheap. Compute power is there. The algorithms have improved. So it's quite possible to do all in all. Now, obviously, you can't mitigate a debris on debris conjunction because you don't have control of either thing. But if you know about it, you can at least try to pre-plan and be sure, have sensors ready tasked to collect in case there is a collision, so that you can quickly try to deal with the situation as it evolves. Okay? And CA processing is very similar to dealing with rendezvous and proximity operations. We're really just talking about how fast things are rendezvousing. Is it a collision, or is it a slow approach where they're just trying to get close to you, either to, in some cases, dock, or at least get close enough to you that you can potentially, for instance, like in the Luch example, do signals intelligence. Okay. Then we have threat analysis. With all this, I now need to understand what is going on with these objects, and are they causing a risk to me? Okay, back up. So we have an updated orbit state. We can now start making threat assessments. Was a maneuver normal or abnormal? Is it the same size, same direction as we always see this week? If so, then that's great. It's a benign maneuver. If it's all of a sudden a 10x larger maneuver than we've traditionally seen, that would be of interest. That's potentially either a threat, or the spacecraft's doing something abnormally for sure, or it just may be that you have a bad solution. And either way, you need to know and characterize that. We take a look at the spacecraft pattern of life so that we can try to understand how this fits in the context of other activities that are going on, and pay particular attention to abnormal maneuvers, because I might want to increase my sensor tasking in response to that to make sure I really start to get a fingerprint as to what's going on. Okay. The abnormal maneuvers may be classified as either hostile or potentially hostile, and you want to understand that. So you may have non-hostile abnormal maneuvers. It says a spacecraft had a propulsion leak, or it started to do a maneuver that went horribly wrong, and now it's lost attitude control, and it may be firing thrusters to try to recover, and so next thing you know, we're getting orbit perturbations that weren't planned. These things happen in real life, and you don't want to raise the red flag and say there's a huge hostile problem when it might just be a abnormal but non-hostile maneuver. It also may just be a spacecraft is getting ready to supersync and go into life. And so it might be doing a large maneuver to start to execute that process. And that can look very much like a drift to a new station location. So you want to keep an eye on that. So this is an example of one way to characterize the pattern of life for an object. This happens to be the Venusat-2 object. It's a geocomsat. And what we can see in the top part of the graph is essentially our measurements, our residual ratios. And we can see there's a history of both the continuous stream of data is from RF sensors processing time difference of arrival measurements. And since they're RF, we can process that all day long, day or night. And then in between there, we have some optical data passes, and you can see those occurring during the night. The large vertical bars are indications of maneuvers that have occurred that we've found and reverse engineered. So we're displaying this to our operators to give them some situational awareness as to this is what the orbit solution looks like for this spacecraft. And then we can actually start to display in the bottom left the maneuvers on what we call the maneuver wheel. So this is a wheel where each ring is a week in time, and then each sector is a day of the week. And as we start to plot the maneuvers that we found looking back over time, we can see a very strong trend for this particular spacecraft. In this case, we can see that the red maneuvers, or the cross-track maneuvers, pretty much occur about the same time every day of the week. And the same thing's true with an in-track maneuver. So cross-tracks occur on Monday, and the in-tracks occur on Thursday. So this gives us sort of essentially we fingerprinted this object now, and we can go into each week kind of expecting that it will maneuver like this. And if it doesn't, that's of interest to it. We want to understand why. And we can also see sort of the box that it's staying in terms of latitude and longitude. And that allows us to characterize what do we think the operational station keeping box for this spacecraft is versus what might actually be published. So once we have our updated orbits, and then we have to assess, is this spacecraft potentially a threat to anybody else? And so again, you have to go through, walking through all the analysis, trying to figure out, as I predict forward where the spacecraft is going, will it be coming near to somebody, or is it plane matching or doing something else? And again, this is the kind of process you need to automate, because you might be trying to scan hundreds, if not thousands, of other objects for potential situations that might be a risk, so that you can then communicate up the channel and say, we think it might be going after X, Y, or Z. So some of the tools that we've developed allow us to do this and start to say, we can start to effectively screen and say, we think this object may be moving and trying to rendezvous with different ones based on certain criteria. And we can start to trend that and see how that evolves every time we get new sensor data. Okay. So then we have to figure out what kind of engagement might be going on. Is this a kinetic engagement, meaning is it actually trying to intercept me? So if it's getting close and the closing velocity is 1 kilometer per second, that's a kinetic intercept. If the closing velocity looks like it's 1 meter per second, that might be trying to do more of a rendezvous or just coming in close. We also want to understand the relative geometry as it's getting close to us. Is it approaching from such that the sun is behind it, so that if it has an optical payload and it's looking at the object, is the object it's looking at well lit? So understanding that gives you insight into potentially what this object is trying to do and what its intent might be. Okay? And then we want to understand how fast that timeline is going to evolve. Because as I come close, I may just be flying by, or I may be just trying to park right next to you. Okay? Because that then informs how I want to potentially schedule my sensors to task. Because if I think it's going to come close and try to slow down, I might be wanting to increase my tasking during those time periods when I think the maneuvers might be occurring. So given all this, then you've now trying to figure out what are your courses of action that are open to you. Okay? And you have to do this again in a timely manner, because every step in this process takes time, which means that that's time while you're trying to figure out what to do that the other person may be changing what they already are doing. So you need to be able to automate the analysis, be able to run through all the options, evaluate your strategies, whether it's, say, for instance, I want to do a maneuver, great, how much and what direction, what do I want to do? Do I need to improve my orbit accuracy because maybe I don't trust that I have a good enough solution to make a decision? Then I need to get better sensors and more tasking. Is there a way for me to deny the other operator observability of where I am? So can I take some strategy? Can I maneuver and get out of his field of view? Can I maneuver and get out of and blow up his OBS association routine or his ability to do maneuver detection? And then, of course, the more you know about what your adversary's capabilities are, the more effective your strategy can be to doing this. So you have to, but again, it's all about execution time and running through these options in a timely manner. Okay. And then you actually have to execute the course of action. The challenge here is you have to have approval to execute that COA, and how long does that take to get? So some decisions might be able to be done at a very low level. Other decisions could require very high levels of authorization because it could be potentially an act of war or some other really critical activity. There's certain UN conventions and treaties and things like that all have to be understood. And you don't want to be known as the person who pulled the trigger too early and did something catastrophic. So once you execute your COA, the process repeats over and again. And one of your courses of action may be to do nothing, and that's okay. But the process repeats, and we execute the OODA loop over and over again. The faster you can compress that, the more effective you are. And the more you can deny the other person the ability to execute their OODA loop, the more effective you will be at executing your mission. So in summary, we've taken a look at, so the OODA loop from the classic fighter pilot definition, I tried to map it into the space domain and how it maps to the different activities that we're typically doing. We've looked at a couple of the flaws or opportunities to improve in each of these areas and some lessons that have been learned over the years. And then it's always worth going through and building up a timeline for your particular systems to say, where am I spending time on each of these activities? Because it turns out if it takes you 6 or 7 hours to execute the tasking all the way to maneuver, over determination and maneuver processing problem, that may be too late. By the time you have enough information to act, your execution time is insufficient to actually protect yourself. And you need to understand what those timelines look like and how they evolve to identify opportunities to improve your process. And at the same time, you want to understand the other actors' OODA loop timelines to see if there's ways to disrupt it. Okay. So the challenge, there's a lot of steps. Each of them take time, and time wasted is time that you're potentially vulnerable. So you want to improve that as much as you can. I started off talking about our top 5 recommendations. Again, I'll revisit them briefly here. Better sensor scheduling to get you the data that you want to collapse the orbit uncertainty, to get you the timeliness of your solutions. Use all the data. Don't throw away anything. Solve your communication challenges with trying to get data into a central place to integrate it. There's always an opportunity for better math. Better math needs better algorithms, which means more effective and more timely solutions. And that allows you to do threat analysis and prioritization more effectively. And then what you want to, and then you can then evaluate your courses of action and execute them quickly. So in the context of what we've been doing here at AGI, these are the lessons that we've learned. And then what we've, of course, then tried to do is develop products that assist with each of these problem areas. So as you look at, for instance, orbit determination and maneuver processing, that gets into our orbit determination toolkit and MPT algorithms. You get into conjunction assessment and threat assessment. Again, we've got products and algorithms oriented around that. And the list continues. So as we try to take a hard look at each of these, try to figure out where do we think people are spending time, where are there opportunities to improve this, and then try to make sure that we've got a product suite that supports this type of a problem. And that concludes today's presentation. Thank you very much.